Welcome to this lecture about CLIC and the transformer. CLIC stands for the Compact Linear Collider, and it's a proposal for a new collider after the LHC. And the main purpose of the LHC is to find the Higgs boson. There are some problems about the LHC, so to say. And one of the problems or challenges is that the colliding particles are protons, that is, they are composed of quarks. And what actually collides are the quarks, as you see here. So a very high QCD background will be seen, and therefore it's harder to find new particles. It's harder to distinguish a peak from the background. And a solution to this could be to collide leptons. Leptons are not compound particles, they are fundamental. And when you collide leptons, you don't have this problem about the background, as what goes into to the collision is actually what also comes into the interaction, as if you see it as a Feynman diagram. But there is a problem about this, about building, for example, a circular E plus E minus collider, because we need to go to very high energies, and as you know from the reading assignment that I gave you, there are these problems has to do with the loss of energy. So I'd like you to now write just a 1-minute paper from your reading assignment, saying what is the challenge, the main challenge of building a circular E plus E minus collider reaching energies higher than a few hundred GeVs. Also, what would be the solution to this problem, and what are the challenges of the solution that is found in this reading assignment. Yep. There you go. So, from now, and I have the time here, and that was 1 minute. It's not a lot of time. Now I'd like to just answer these questions on class. So, Lucas, do you have what is the main challenge of building such a circular collider?
The problem that you have when you have the circle, you have a lot of single radiation.
Yeah.
And if you are working on this energy, you probably lose a lot of energy.
Okay.
I think.
Yeah. So, do you know why it is, why you lose more energy when building an E plus E minus collider than when building a collider with, for example, protons? Any suggestions? Okay, so the thing is, if you look at page 5, you see equation 1, that the energy loss is, so that is the power radiated, I've written there, is proportional to the energy to the fourth divided by the mass to the third. And if you go to very, very high energies, you see that the energy, this ratio goes up a lot. It is increased a lot faster if you have a very low mass than if you have a high mass, because the power that is lost is proportional to the mass to the third, and therefore it is a very good thing to build to sort of to build circular hadron colliders where you have a high mass and you can reach very high energies. But obviously you have the problem about, as we talked about before, that the hadrons are compound. So what would be the solution to this challenge? If you need to have the advantage of colliding leptons that are fundamental, but you don't want to lose a lot of energy when accelerating them in a circular collider. What would be the solution to that? Obviously,
Build a long linear collider.
Build a long linear collider. And what would be the challenges about such a linear collider?
It has to be really long.
It has to be really, really long for it to.
And you can't reuse it, right?
No, you cannot reuse the accelerating structures as you can when the particles pass the same point every time they go around the circular collider. You need to reach this very high energy within a very short distance. That is done, for example, at the compact linear collider, where the nominal acceleration gradient is 100 megavolts per meter, and you'll be able to reach 3 TeV, center of mass energy, within some 50 kilometers. That is within a reachable sort of distance. But to do this, you cannot use the conventional RF structures to accelerate the beam, because the structures will break down as you apply very high voltage to the structures. So therefore, the proposal is like this. You have a drive beam and a main beam, and the drive beam is actually used to accelerate the main beam. So when you decelerate the drive beam, you can transfer the power and accelerate the main beam, and build up the voltage differences along the accelerating structure like this. Yeah, will look like this. So we have the drive beam coming here, and the wave fields are built up, and they are just electromagnetic waves that can be transmitted through this waveguide, and they will be applied to this structure where you have a change in voltage at a certain frequency that will accelerate the beam. So how can you really explain this, what happens? You can explain this by for example, looking at this transformer. Not this transformer, but a normal transformer as we know it. And I'd like you to just build a transformer, and then you should be able to calculate what is the voltage. So I want you to so what is the voltage coming into the transformer, and what is the secondary voltage that comes out of the transformer. So this is compared to what is the voltage that is induced sort of in the drive beam, and what voltage can you apply over a certain distance at the main beam part. And please.
One is on the other side 250.
Okay, so we have power on this one.
Yeah.
Let's go here.
I think you would like to use this one, because what you would like is an alternating current.
Yeah, sure.
Because you need the magnetic flux to be changed
Yeah.
inside this
Sure.
core.
Okay, so we have 3 entrances here.
Just the outer ones.
Yeah.
I found out.
Okay. And we want to measure the voltage coming in. Yes. No, but it is. And the voltage coming out.
What would you expect?
So according to Lenz's law, that we could, if we have 250 windings, we have 4 times the amount of windings over here, we have 4 times the voltage.
Yes, exactly. And so we can just write this on the blackboard. So what you use is that from Faraday's law, you have that the voltage is equal to the number of windings times the change in magnetic flux. And if you apply this equation to both sides, you can reach the equation that is this. Oh, sorry. And you see exactly that you should be able to measure 4 times the voltage at the other side. And also, if you assume that the power transfer, that the incoming power is equal to the outgoing power, then the current on one side divided by the current on the other side is related to the other quantities like this. And that is, if you have a high current in, for example, in the so this is the overall schedule. So if you have a high current in this drive beam, you can extract the power to the main beam, and you can accelerate. You will have a higher voltage difference in this side than in this side, and you can accelerate a lower current, that is a lower amount of electrons, you can say. But how do you create this high beam, this high current beam here? To create a very high current beam, you need a complex where you just accelerate a beam in the normal way, and you can combine bunches of, for example, electrons into doubling or quadrupling the frequency, and if you have the same number of electrons in each bunch, you will also increase the current. Let's have a look at this small video here, where you actually see what happens. So here the electrons are not electrons or bunches of electrons, but they are small lemmings walking indicating each of these bunches, and they have a very specific time structure for exactly this to happen, that some lemmings go around and the next 4 lemmings continue, and they will combine into this beam, go around here, and the next bunches of lemmings will come into this ring, which is called the combiner ring, and at the end you will be able to extract a beam of lemmings. You see now that the last lemmings will just fit in here, and at the end you have a very, very high intensity beam that you can use to accelerate the main beam using the power extraction transfer structures.